Alright, so let's look at this question. So we have questions on distinct symmetry operations and symmetry elements, right? So the first question here states that list the symmetry operations that can be generated by C4 and S4 symmetry elements. So basically, you have to note that symmetry operations will leave the molecule indistinguishable from its original configuration, right? So let's say we have cyclobutane. Let's call this 1, 2, 3, 4, and let's say we carry out C4 operation on this. So basically, we are going to have this comes here. We're going to have 1, 2, 3, 4, right? So basically, these two molecules are indistinguishable. They are not different from each other. We only changed the positions of the carbon, right? So symmetry operation has been carried out successfully here. So let's say we have a water molecule. So we have water to be this, right? And let's say this is the we have this to be the C2 axis, right? This is the C2 axis. So let's say we carry out mirror plane on it, right? So this is 1, this is 2. Let's carry out this. So basically, we're going to have H2 and H1. So basically, this structure is still the same as this. It's indistinguishable from this, right? But let's say we have CN. Let's call this triple bond, and let's say we carry out mirror. Let's say we carry out sigma V on it. So we have this here, sigma V. So basically, we're going to have Cn give this, right? So basically, this is not a symmetry operation in this molecule, because these two are different, so they are distinguishable, right? So basically, symmetry operations will leave a molecule indistinguishable from its original configuration, and symmetry elements are points, axes, or planes through which symmetry operations can be carried out. So now the question says, how many symmetry operations can be carried out to reach the identity? But basically, looking at the question here, list the distinct symmetry operations that can be generated by C4. So what we're trying to say here is that how many symmetry operations can be carried out on in order to reach identity. Looking at this here, we have to carry this one out 4 times in order to return back to the original configuration, right? So, but let's look at it. C4. If we carry out C4 once, we're going to have C4. If we carry out C4 twice, we're going to have this one cancels this, and therefore we have C2. If we carry out C4 thrice, we're going to have C4 3, and if we carry out C4 4 times, we are going to have identity. So it's also the same as this that we drew the other time. 1, 2, 3, and 4. The first C4 gives this. We have it to be 1, 2, 3, 4. So the second C4 gives let's call this second C4. It gives this, right? We have it to be 2, 3, 4, and 1. So, and the last one gives let's call this C3 rather. So we have this to be 1, 2, 3, and 4. And let's see the last one, C4. It gives back the original configuration to be 1, 2, 3, 4. So it gives the identity. So basically, we're asking how many times can this operation be carried out in order to bring back identity, while still maintaining the structure at every step, or at every stage. So that's that. So also for Sn, right, improper rotation axis, it is successfully made up of rotation and reflection. So we have Sn to be basically a combination of the sigma h, which is the reflection, the horizontal reflection, and then Cn, right? So from the question, let's look at the question again. So we have in the question S4, right? So now let's look at this S4. So that's going to be S4. Therefore, we're going to have, at the first trial, we're going to have sigma h and then C41, right? Recall that Sn here, if Sn is S4, we're going to have sigma h C4. If this was C3, we're going to have sigma h C3, right? So for this, the first operation we carried out was this, right? So this gives back the S4, right? So when we carry out this the second time, it's going to give sigma h scale twice and C4 twice, right? So when you carry out reflection 2 times, let's say you reflected a particular point. I'm trying to see how I can explain this. So you reflected a tree. Let's say you reflected or this image, you reflected it here, and then you reflected it back again. It's going to give the original structure. So basically, reflection 2 times will give identity, right? And then this one we're going to have C2. So identity times C2 is like saying 1 times C2. So we're going to have C2. So another is this S43. So that's going to be sigma H3 and then C43. So this will give us sigma H and then sigma H twice and then C43. So this will give sigma H and we're going to have identity, and then because this is twice, and we're going to have C43 here. So this becomes, because this is like 1, right? So we have sigma H and C43. So when we multiply rotation and then reflection, right, we're going to have Sn. So this is going to be S43, right? So let's look at the fourth one. We only stop when we reach identity, right? So the next one is this, and then we have C44. So this is going to give reflection basically twice. That's going to be this and this, right? And so this one will give C1. So basically C1 is the same thing as identity. So this one will give identity, identity, and identity. So basically it's going to be identity. So this is the distinct operations are basically S4, which is the first one here. The second one is C2. The third one is S43, and the last one is E, identity, right? So these are the distinct operations there. So there's also a shortcut to get the answer in this case. So we can also use, so you can also say that when n is odd, you can simply say that it gives what? It gives n minus 1 improper axis, right? And then it gives sigma h. It also gives n minus 1 proper axis, right? Proper axis and identity. So it gives this for 1, 2, 3, and then 4 when it is odd. But in this case, we have even n, right? So in this case, n is even. So basically, when n is even, it's going to give, the first one is going to give is n over 2. This improper axis is going to give also n over 2 minus 1 proper axis, and it's also going to give identity, right? So now let's confirm this. We have identity here, which is this C. So NA is 4. So for A, let's look at A. A is n over 2. That is going to be 4 over 2. That is going to give 2 improper axes of rotation. So we have 2 improper axes of rotation here. So let's look at B. N over 2 minus 1, right? So this gives 4 over 2 minus 1. That's basically 2 minus 1. So it gives 1 proper axis of rotation, and that's the C2A, right? So let's also look at this question. So write the symmetry operations generated by C3 and C6 proper axis of rotation. So we basically have C3. The first one is going to give C3, right? So the second one is C32. That will give C32 also. So the third one is C33, and that will give C1, which is the same thing as identity. So let's look at C6. So the first one will give C6. The second one here will give this one cancels out. We have C3. C63 is going to give C2, right? So C64 is going to give C2 and then 3, right? 2A, 3A. So this one C65 is going to give C65, right? And the last one, C6, is going to give C1, which is the same thing as identity. Now let's look at this question. So using S3 and S4, show that an improper axis of rotation, an improper axis of odd order n will generate 2n symmetry operations with this n minus 1 proper and n minus 1 improper. So let's look at this. So basically for the first one we have that odd order number, right? So this is odd order number, even order number. So we are dealing with S3 in the first part. So that is going to be S3 1 to give S3, right? So S3 2 will give S3 2, and S3 3 should give basically is going to give, oh sorry, what we're going to have here, S3 1 is going to give sigma H and then sigma H and then C3, right? So which is going to give S3 as well. So the second one is going to be sigma H square and C3 square, right? So this is going to give identity and then C3 square, and so this is going to give C3 square, right? So the third one is going to be sigma H cube C3 cube. So this is going to give sigma H, and then we have sigma H square, and then we have 1, which is C1 or identity, whichever one. So basically we are going to have this one also. We are going to have sigma H identity and identity. So this will give us sigma H. So the fourth one, S3 4, right? So this is going to give sigma H4 C3 4. That will give us, this one will become identity, that is CHK, CHK, and then we are going to have this, we are going to have C3 C3 4, right? So we're going to have identity, and in this case we can bring this out to be C3 3 and then C3 1, right? So basically we're going to have 3 identities, so that's going to be C3, right? So let's look at S3 5. So that's going to give us sigma H5 and C3 5. So this is going to give us C4 C3 4 and sigma H, right? And then we have C3 3 C3 2, right? So this is going to give us identity, and then we have sigma H This will give us identity. Then we have C3 square. So basically we are going to have this will give us S3 2, right? So the next one is going to be CS3 6, and that is going to give us so let's number 2, 3, 4, we have 5, and this is number 6, right? So this is going to give us sigma H6 and C36. So this is going to give since this is even, it will give identity, and this will give C3 3, and then C3 3. So this will give identity, 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 and that's basically identity. So we cannot stop since we've reached the identity. So now show that it will generate 2n symmetry operation with so it's going to generate 2n symmetry operation. So in the first case here, n is 3, right? So that's going to be 2 3. So that should give 6 symmetry operations, and we add 6 symmetry operations here also, right? So let's look at the proper. So these are these symmetry operations that we add. For this one we add, the first one is S3, the second one is C3 square, the third one is sigma H, the fourth one is C3, right? The fourth one, the fifth one is S32, and the last one is identity. So let me erase some parts. So basically we have identity here. So what we have now is this. We'll be able to confirm that there is 6 of it, right? So 1 2 3 4 5 6. So let's look at the proper n minus 2. That will be 3 minus 1, and that should give 2 proper. So these are 1, the first proper as this, and the second proper, right? So let's look at this n minus 1 improper. So that will be 3 minus 1 to give 2. So improper we have it to be 1, and we have the second one to be 2, right? So these are improper rotation axes, right? So now let's see the second question also. So an improper axis of even order. So we have S4, right? So it should generate n symmetry. So n is equal to 4. So let's see S4 when it's 1 give S4. So S4 when it's S4 when it's 1 we give sigma H and C4, right? So this will give us S4. So we're going to have these two. So it's going to give sigma H square and C4 square, right? So this will give us identity, and this will give us 2 here. So it's going to be C2. So we have C2 here. So let's call this 1 or A, B. So C. So we have S4 3. So this will give us sigma H 3, and we have C4 3. So this is going to give us sigma H square and C4 3. So this is going to give us sigma H identity and C4 3. So we're going to have S4 3. So let's look at D. So D is going to be S4 4, and that will give us sigma H4 C4 4. And so sigma H4 is even, so it's going to give identity, and this one also cancel out to give C1, which is also identity. So we already reached identity, so we can stop. So this is confirmed already. So now let's look at the other one, n minus 2 to give proper and improper. So let's list out the symmetry elements. We have S4, we have C2, we have S4 3, and we have identity. So proper axis of rotation is going to be 4 over 2 minus 1. That will give us 2 minus 1, which is 1. So proper axis is this, just 1. So improper axis is basically n over 2, and that will give us 4 over 2, and that will give 2. So we have 1 and 2. So basically proper axes are represented by C, N. Improper axes are represented by S, N, right? Looking at this question, which of the following compounds has S4 axis? So basically, this is basically this. We have a structure to be this, right? And we have different symmetry elements there. So, but for us to have this, there must be C4, right? At least there must be C4. So in this case, there is no C4. There is no C4, right? But let's look at the second structure. So this second structure is tetrahedral, just like methane. So we have it to be this. So we have it to be this and this, right? So it's more or less like a structure like this that has this, and this one is pointing like outward, right? So if you try to write out the symmetry element for this, we have it to be identity. We have it to be 4C3. No, C3 is when we have an axis through this one, we're able to carry out C3, an axis through this one, C3, an axis through this one, or a point rather through this one, a point through this one, we're able to carry out C3. So it also has 3C2, right? So you can carry out C2 from when you want to carry out C2, two positions will be constant, right? And then you have the axis. So basically we have 3C2 here, and we also have 6 sigma V, and we have 3S4. So basically this one has S4. Just take note of this, try to know it. But in your exam, which of the following compound has S4? You may want to first write all the elements that I wrote out here, and then write the element of this, right? Alright, so this question, pyridine and pyrazine were put in separate sample bottles labeled A and B respectively. So this is A, this is B, right? So the first question is identify all the symmetry elements in each compound. So let's see A. So basically we have it to be this nitrogen, we have it to be this, right? So let's check for the first one. The first one is identity. Is there identity here? Yeah, sure. Every molecule, every structure has an identity, right? So the next thing is properties of rotation. So the only properties of rotation we have is this, right? This through this point. So we have a C2 here. This is C2, right? So there's C2 here also. So what else again do we have? So let's look at the mirror plane. So basically we can have a mirror through this point. Yeah. So we can also have a mirror that cuts through downwards, right? So basically the symmetry elements are identity, C2, sigma V, and sigma V prime. So let's look at the second structure. We have it to be this. So this is the second structure. We have nitrogen and then the bonds here, right? So the first thing, identity is possible, right? Let's write it underneath here. So identity is let's write it here. Identity is possible, right? So let's put this B. So the next thing is, let's check for proper axis of rotation C. So we can have C2 here, right? So we can also have C2 here, and we can also have C2 here. So these are different points of C2. So we have 3 C2s, right? So let's look at mirror. So mirror, we can have mirror here, right? So that's, let's call that sigma V. So we can also have another mirror here, right? We can also have another mirror here, right? So we also call that sigma V prime. So because this is not, let's look at it here. So what is here can also be seen at the other side. What is here can also be seen here. What is seen here can also be seen here. Just like how do I put it? Just like in hydrogen peroxide, the trans. What if you pass through the middle? What is here? You will see it here. So that's the same here. So therefore it has that's identity, right? So these are the symmetry elements for this, right? So identify all the symmetry elements in each compound. So we'll be able to identify for A and for B. So which of the compound has higher symmetry? So compound B has higher symmetry. So which of the compounds A or B has the same set of symmetry as water molecule? So let's look at it. Water molecule is this, right? We have water molecule to be this. So this is 1, this is 2. So identity, is there identity here? There's identity. So let's look at properties of rotation. The only properties of rotation here is C2, because if you rotate this, this will come here, this will come here. So we have C2, right? So which one again? Let's look at mirror. So the only mirror we can have here, we can have this that cuts through, right? We can have this that cuts through, and we can also have this that cuts through also, like in this way. So basically we have sigma V and we have sigma V prime. So which of the compound A? Definitely compound A has the same symmetry element as water molecule.